Alright, in this video here I'm going to talk about Newton's law of cooling. Now in this one I'm just going to talk about the formula for Newton's law of cooling and what all the different variables represent, and then I'll do another video where I actually go through an example problem that involves Newton's law of cooling. Right, so Newton's law of cooling, what it involves is you have a hot object, like let's say you have a hot cup of coffee. You place it on a table in a room where the temperature is, 70 degrees. Let's say the cup of coffee was 200 degrees. You place it in a room that's the surrounding air temperature is 70 degrees. Newton's law of cooling describes what the temperature of that coffee is going to be as it cools down and comes into equilibrium with the room temperature. That's what Newton's law of cooling is all about. All right, how long it takes something to cool depending on the surrounding air temperature. All right, so the formula for Newton's law of cooling, capital T of T, right? So the capital T stands for the temperature, the lowercase t stands for time, right? Can be confusing because they're both the letter T, but one's capital, one's lowercase. The lowercase t is for time, capital is temperature, right? So T of T equals T sub s plus D sub 0 e to the negative kt, right? Now, what does all that stuff mean? Capital T of T means the temperature of the object at time t, right? The object being like the cup of coffee that you're putting in the room. So it would be the temperature of that object at time t. All right, T sub s is the temperature of the surroundings, right? So if the room is 70 degrees, 70 is your T sub s, right? That's the temperature of the surroundings. D sub 0 is the initial temperature difference between the object and the surroundings. Right, so if the cup of coffee, I don't remember what I just said, the cup of coffee was 200 degrees and the air temperature in the room is 70 degrees, D sub 0 is 130, right? That's the difference between 200 and 70, right? So that's that D sub 0, that's the not just the initial temperature of the hot cup of coffee, the initial difference in temperature between the hot cup of coffee and the surroundings. All right, so that's a key thing, which if you saw some of the videos that I did about, exponential growth, population growth, or radioactive decay, that number in front of the E was usually the initial amount. In this case, it's not exactly that. It's not the initial temperature of the coffee. It's that difference between the object and the surroundings, right? K represents some positive constant, and it depends on the object that you're dealing with, right? If you have a cup of coffee, if it's just in like an open cup, it's going to cool at a different rate than if it's in a closed thermos or if it's just spilled on a table, right? So the object that you have, determines what that constant K is, and you would figure out that constant K by doing experiments and seeing what goes on, when I have this thing at this temperature and all that stuff. But in most problems, that K is either given to you or they give you enough information that you can solve and figure out what K is. Right, and then T represents time, and for time you can use any unit of time. It can be minutes, it can be hours. Generally, usually we don't use like years and stuff like that for Newton's law of cooling. It doesn't take years for a cup of coffee to cool off when you put it down in a room that's 70 degrees. It takes minutes or hours or something like that. But you can use any unit of time when you're dealing with the T here. All right, so that's Newton's law of cooling. That's what all of the variables represent. And so I'm going to stop this video here and then do another one where we go through an example problem and actually use Newton's law of cooling. So make sure you check out that video so you can actually see how this formula works when you're using it to try to solve a problem.